Okay, so in this video, we're going to be looking at how to solve for an interpolating polynomial. And the basic idea here is that I have a set of points, and I want a polynomial that's going to pass through the set of points that I've been given. Now, I've just kind of made these points up, so I'm not necessarily expecting to get a really nice polynomial with integer coefficients or anything, but that doesn't really matter. The process will be completely the same. Now, the idea basically is that I'm going to create a system of equations that is going to give me enough equations in my system that I can solve for all of the unknown coefficients. And the general rule is that for each degree of the polynomial, n, I need n plus 1 points to find an exact polynomial that passes through all the points. Now, if I have fewer points than I require, the n plus 1, so like for a cubic polynomial, I would need 4 points to get an exact polynomial. If I had fewer points than I needed, then what would happen is I would get a dependent solution, and I would have an infinite number of polynomials that would pass through those points. I would have to choose one of the coefficients, and then I could force the rest of them to be something in particular. If I have more than n plus 1 points, then the chances are I'm not going to find any polynomial that goes through all of the points. And at that point, I would be doing a polynomial of best fit. You're ending up in statistics at this point. So you probably won't get an exact polynomial that fits through all of the points. You will just need to get some kind of projection or something that gets as close as possible. But if you have exactly, for instance, for a quadratic equation, you need exactly 3 points, then we can find an exact polynomial that's going to pass through all 3 of these points. Now, again, the main idea here is we're going to set up a system of equations. So for my first point, I'm going to plug that in for x, and then I'm going to set my other side of the equation equal to y. And so if I plug in 1, I'm going to get a times 1 squared plus b times 1 plus c is equal to 2. And if I plug in my second point, I'm going to get 3 squared, so 9a plus 3b plus c is equal to 5. And then finally, if I plug in 5, 1, I'm going to get 25a plus 5b plus c is equal to 1. So these are my systems of equations. And so I'm going to need to set up a matrix that I can solve. So 1, 1, 1, 9, 3, 1, 25, 5, 1, and on the other side, 2, 5, 1. Now we can go ahead and then solve this problem using any method that we like for solving a system of 3 variable equations. I am going to use technology, since I have other videos where we go through the process for solving a system. And I'm just going to put this in my calculator exactly as it is written as a 3x4 matrix. And then I'm going to row reduce it. And the result of row reducing I'm going to end up with so I went to reduced echelon form since I was using technology rather than trying to back solve. So -7/8. And for this one, I got 5. And for this one, I ended up with -17/8. And so it turns out that my corresponding polynomial is going to be -7/8 x squared plus 5x minus 17/8. And I could go ahead and plot this with all of the points to make sure that that in fact does work. And so if we go to Desmos, we can plot all 3 points on our graph, and we can see that, yes, indeed, here are 3 points, and this is the graph of our polynomial that we found, and it does in fact go through all 3 of our points.